So today we will discuss some electronic configuration oxidation state of p block element. Since we all know p orbital can maximum accommodate of 6 electron, so there are 6 group in p block element, that is group 13, group 14, group 15, group 16, group 17 and group 18. General electronic configuration of group 13 is ns2np1. For group 14 it is ns2np2. For group 15 it is ns2np3. For group 16 it is ns2np4. For group 17 it is ns2np5, and for group 18 it is ns2np6. The first member of group 13 is boron. For group 14 it is carbon. For group 15 it is nitrogen. For group 16 it is oxygen. For group 17 it is fluorine, and for group 18 it is helium. Group oxidation state of group 13 is +3. Group oxidation state for group 14 is +4. For group 15 it is +5. For 16 it is +6. For 17 it is +7, and for 18 it is +2 as well as +8. The elements showing other oxidation state are +1 for group 13. For group 14 +2 and -4. For group 15 it is +3 and -3. For group 16 it is +4, +2, -2. Sometime it is -1, +1, -half, as we all know in the case of peroxide, superoxide, which is already discussed. And the halogen will show group +5, +3, +1, -1 oxidation state, and group 18 will show +6, +4, +2 in their combined oxidation state. When they are in combined form, they will show some different oxidation state rather than their group oxidation state. So coming to the next point, that is nature of element. So p block is the block in which metals, non-metal and metalloids, all three are present. As we move down the group, metallic character increases, or we can say the non-metallic character decreases while moving down the group. As we move down the group, metallic character increases and non-metallic character decreases. So the metalloid present in p block are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine. These are the metalloid present, and p block is the only block which contain metalloids. Now coming to the nature of oxide, as we all know, the oxide of non-metal are acidic in nature, and the oxide of metal are generally basic in nature, as we studied in our class 10 also in the chapter metal and non-metal. So the acidic nature of oxide decreases down the group. As the non-metallic character decreases down the group, so acidic nature of the oxide decreases down the group, and basic nature of the oxide increases down the group. As the metallic character increases down the group, so the basic nature or basic character of oxide increases down the group. Talking about the nature of compounds, so we all know when a highly reactive non-metal and highly reactive metal combine together in a chemical reaction, the compound form is an ionic compound. Okay, so let us take an example where aluminum is reacting with chlorine gas, so it forms AlCl3. So it's an ionic compound. You can take the other example of NaCl as well, sodium chloride. So when an highly reactive non-metal combined with highly reactive metal, we get an ionic compound. Why it is so? Due to the large difference in electronegativity value, we are getting an ionic compound. When two highly reactive non-metal combine, they generally form covalent compound. Okay, when a highly reactive non-metal combined with highly reactive non-metal, then they form covalent compound. Ionic compound will have complete transfer of electron between them, means they have electrovalent bond, but covalent compound will have covalent bond between them. Okay, so the example is when we react hydrogen gas and chlorine gas together, HCl is formed, that is hydrogen chloride. Remember, when HCl is in gaseous form, we call it as hydrogen chloride, and when it is in aqueous form, we call it as hydrochloric acid. Always remember this point. Coming to the point, anomalous behavior means the different behavior of the first member of each family. Okay, so the first member of each family, these are the first member: boron, carbon, nitrogen, oxygen, fluorine, helium. These are the first member of their family. They show some anomalous behavior, means some different behavior from the rest of other member which are present downside of them. It is majorly due to the following reason. The first reason is their very small size. And the second reason is there is no vacant d orbital present in it. They are showing anomalous behavior due to the following reason. Okay, the first reason is very small size, their size is very small, and they don't have vacant d orbital. They have only 2s and 2p orbital. They don't have d. Since the principal quantum number is 2, the orbital present is s and p, as we all studied in your atomic structure. I have taught. So the d orbitals are not present in the first member. That's why they are showing some anomalous property. And there is one more reason, that the electronegativity of the first member is little bit higher than other. So these are the reason why the first member of each family is showing anomalous behavior. Okay, let us take an example. Since the d orbital is absent in boron, it is the first member. Okay, so Bf63 minus doesn't exist. Since it is not having d orbital, it can't extend to the further orbitals. But AlF63 minus can be exist, because aluminum comes after boron in family. It have vacant d orbital, so it can accommodate more ligand by holding the negative charge. So due to the absence of d orbital, Bf6 minus doesn't exist and AlF63 minus exists. So due to the absence of d orbital, they form p pi multiple bonds. Okay, they form p pi bonds. They form p pi. Who are they? The first member of each family, and the rest form p pi d pi or d pi multiple bonds. These are the type of pi bond which we have already studied in our chapter 4, that was chemical bonding. So you are all aware of that. So thank you very much, student. We'll continue our next topic in our next video. Till then, bye bye, take care everyone.